In this video, I'm going to talk about a search algorithm called Heuristic Search. Now, Heuristic Search is used on graphs to find a path from one position to another, or to search from one node along the edges to another node. An example graph might look something like this. And one common problem that we see with either breadth first search or depth first search is that the way that it traverses through the nodes is a little counterintuitive for how we would imagine it as humans. So if I had a start location as this node here and a goal location of this node here, and I were to run a breadth first search algorithm on this node, it would start here, and then the next three nodes it would check would be all three connections. This one, and this one. Now, one thing you might ask yourself is, well, why are we even bothering to check this node? This node is obviously further away from the goal than this node or this node, so let's check those two. And even worse off, after we check this first and second node here, these are going to add this connecting node, and this connecting node into our frontier of nodes to explore. But even though those nodes are in the frontier, it will still explore this node first before exploring even this node over here. And this one's really close to the goal. So, using the idea of a priority queue for our frontier, we can use what's called a heuristic function. And that's where this word heuristic search comes from. That's where this word heuristic is. A heuristic function is a function that means, well, it's not the exact answer, but it's close to the answer, right? So typically, a typical heuristic function used for a search on a graph might be something like a distance. So just writing out some pseudocode here, if we had a function called heuristic and it took two nodes, A and B, this function could just return some sort of distance between the two. The distance between A and B. The greater this distance, the larger this heuristic function would be, and the further back in our priority queue it would put our nodes to explore. Let's think about how this would work in practice. If we were to explore from our start node and search to our goal node, right? This would be the very first node that we put into our priority queue, or our frontier. Remember that our frontier is the list of nodes that we're going to explore next, right, as we explore outward through this graph. So first we put our start node in here, and then it would immediately put nodes 2, 3, and 4. 2, 3, and 4. Now, because we're using this heuristic, and because we're turning our frontier into a priority queue, we could associate the values, or some value, with each of these nodes in the priority queue. In this case, if we use this heuristic function, it means that this node here, too, has the smallest distance, so it will have the smallest value here in our frontier. Let's put some random numbers in here. Well, not so random, but let's put some example numbers in here. Let's say the distance between 2 and our goal has a value of 5. That means that here in our frontier, this would have a value of 5. Let's say the distance between 3 and our goal is a value of 6, right? This is just the distance between these two node positions. So this has a value of 6. This has a value of 6. And let's say the distance from 4 to our goal, this total distance here, is a value of 8. It would look something like this. Now, according to our priority queue, this could return back the node with the lowest priority. So what node would we explore next? Well, we would explore 2. 2 would be the next one we explore because it's the lowest value, right? This one would be eliminated. When we go to explore node 2, we would add this node here, node 5. Because it's the only new connected node that 2 has, right? 5 would then be added into our priority queue, node 5. And let's say that this has a value of 2, or a distance of 2. So the value here in the frontier that it would be associated with is that distance 2. Then the next thing that would happen is we'd say, okay, what's the next node we should explore? Well, based on our frontier, this node here, 5, with a value of 2. This has the lowest priority, so it's going to be the next node that comes out of a priority queue. So now we're going to explore the node 5. When we explore the node 5, we find that we're connected to our goal here, 6. And we're also connected to this other node, 7. 6 would be added into our frontier, and 7 would be added into our frontier. And then when we ask this heuristic function, what's the distance from 6, our goal node, to our goal? Well, the distance is 0. It is the goal. 7, say this has a distance of 5. Finally, we'd explore the last node here. We'd say, well, what's the next node to explore in our frontier? And it would be 6, our goal node. At that point, our function would end. We found our path. According to this heuristic search, with these values, we would have explored node 1, then node 2, then node 5, and then node 6. Notice how it took a path directly to the goal, right? At least what it thought was the path closest to the goal, just based on the distances. Now, a heuristic search like this can have a lot of optimization, a lot of benefits over something like a breadth-first search. Remember that breadth-first search would go out in all directions evenly, which is why I would have explored this node 4 before exploring this node 5, right? One issue that heuristic searches do have is that based on your heuristic function, if you're using the common one, like this, which is just the distance between the current node you're going to explore and the goal node, then one issue you may run into is an issue like this. Say, for example, our nodes are actually connected, not directly through 5 and 6, but they're actually connected something like this. Now, this heuristic search function would not be able to find a path directly to the goal in that case. Remember that it's always going to explore the node that is closest to the goal, because that's what our heuristic function is. In this case, our heuristic function would probably end up exploring node 1, node 2, node 5, and then it would probably explore 7 because it's the next closest node to the goal. Then it would probably explore 3 because it's the next closest to the goal. Then it would explore this one, and then finally explore our goal node. Now, in this case, our heuristic search may end up with a performance that's similar to breadth-first search because it's exploring almost every single node in our graph. However, note that we're still optimizing out node 4 here. This would essentially be like a worst-case scenario. So in the worst-case scenario for heuristic search, it will perform as poorly as breadth-first search. But in the best-case scenario, it can find you a path that's almost directly going to your goal.